In previous videos, we've looked at ways in which we can do offline analysis of the amplitude envelope or frequency content of audio, and how we can use this to affect parameters and events in games. This is an efficient way of working since we're not trying to analyze the audio in real time, something which can have significant processing overhead. However, if the audio is changing in real time, for example, if the volume is varying or effects are being applied to it, then the cooked data from an offline analysis is of little use to us. In this video, we'll look at an example of how to implement real-time analysis of audio. You may remember that in our first example of envelope analysis in a previous video, we used the fairy who was in the cave at bookmark 6 in the demonstration project.
I came down here looking for my friend and now I can't find the way out.
In this case, we enabled envelope analysis on each sound wave within the sound queue.
I came down here looking for my friend and now I can't find the way out.
Then we got this cooked envelope data and we used it to adjust the particle system, static mesh and dynamic material of the blueprint so that these changed in response to the fairy's speech. Since the fairy's speech comes from the location of the fairy itself, then we didn't need to think about any amplitude over distance changes, and there are no effects applied to the sound, so we know that the cooked envelope data will accurately reflect what we're hearing. This time we're going to be looking at a sound that does change in real time, so we're going to use real-time analysis via the on-audio multi-envelope value node. This gets the averaged envelope value across all playing sounds on an audio component. We'll start by going to our blueprints folder and making a new blueprint that we'll call wind tree. So it's an actor class, wind_tree, and we'll open that up. We'll add an audio component and we're going to use the sound cue called trees wind01. We're going to override its attenuation and we'll start by setting that from 400 dropping off to 3000. We'll go just behind the lake area over here and we'll drop that blueprint into the level. What we want to be able to do with this blueprint is to be able to drop it into the level anywhere we like and for the wind audio to affect the leaves on the trees. So when it's windier, the leaves will have more movement. Since this sound cue is using envelopers to vary the sound, we're going to need to do the analysis of this amplitude in real time. In the event graph, with the audio component selected, I'm going to get events on audio multi-envelope value. This node gives us the average amplitude envelope on the audio component, so we'll get the amplitude of the sound that results from the combination of these two sound waves. Let's set this to a variable so that we can easily access it elsewhere in the blueprint, and let's see the values we're getting out via a print string. So they're going up to nearly 0.01. Well, there was a 0.011 then. Okay, so that's the kind of general range we're getting. Now we want to affect any trees that might theoretically hear that wind sound. So back in our blueprint, we're going to add a sphere collision component. Then we're going to get the attenuation settings of the sound itself to determine the size of this sphere. Getting a reference to the sound, we'll get attenuation settings. We'll break that struct. Then we'll find the attenuation extents vector here, and we'll break that. So the extents are where the sound is at its maximum volume, and since it is a sphere, we only need to look at x. What we're going to do is we're going to get x, and we're going to add it to the fall-off distance. This will give us the total radius within which the sound might be heard. So let's set that to a variable that we'll call radius. And we'll do all this on event begin play. Having got the radius within which the sounds might be heard by the trees, we'll get that collision sphere and we'll set radius. Let's just make that sphere visible in game. So we'll turn off hidden in game and just check that it is actually matching the radius of the sound. So there we can see it in red here. And if we go back to our sound itself and change the fall off distance, let's set that to 1000. Play the game, we should see that the radius is now updated and is now much smaller. Next, we want to find all trees that fall within that radius and add them to an array so that we can act upon them. So dragging out from our collision sphere, I'm going to get overlapping actors. And the class I'm looking for is called BP tree. We'll use a for each loop to read through each element of that array. And we want to pass variables to a custom event within this blueprint here. So we don't want to store an array of actor object references, which is what we'll get here. We actually want to cast to each of those and return a reference to the blueprint tree objects themselves. Then we'll add them to a new array that we'll call trees. Again, let's check that that's all working so far. So another print string here, and what we'll do is we'll get the display name of each tree. Just set that duration so it's slightly longer, so we've got time to read through it. And for example, in the level, we've got this tree that is called BP tree 270. So when we play, hopefully we'll see that has been included in the array. And there it is, about halfway down. So let's turn that off, and we don't need that anymore. So now we've got all our trees in a nice array. What should we do with them? Well, let's go and have a look at this blueprint class here. And within it, you can see we've got this custom event, and that's got inputs called wind speed and wind intensity. Now this tree crown here is set up in the construction script, and for the wind speed we want values between 1 and 2, and for the wind intensity we'll want values between 1 and 3. So this is our setup or initialization, and then when the sound actually starts playing, we want to read through that array of trees and access that custom event within them. So we'll use another for each loop, and we'll add each element to a variable which we'll call current tree. And then getting a reference to that, we're going to set wind param, which you might remember is the name of the custom event within our tree. So our wind speed is looking for a value between 1 and 2. So we'll get a reference to that average envelope value. It's the real-time value of our audio component. And we'll map that to range, clamped. And we'll set that from 0 to 1 and then add 1. So we get that range between 1 and 2. And the input range, when we had a look at those figures, is quite low. So I'm going to set this range here to 0.005. Similarly for our wind intensity, again, get this reference, map range, clamped. Same range going in, 0.005. And this time for the wind intensity, we want numbers between 1 and 3. So we'll map those between 0 and 2. And again, add 1. Just neaten that up a little, and then let's see what that does. So you can see that the envelope of the audio playing on that sound cue is affecting the movement of the leaves on those trees. But only the trees that fall within the radius of that sound. So if you look at trees that are further away, they're not moving. Okay, so let's go over that again. When the game begins, we look at the audio component and we get its attenuation settings. We add the extents to the fall-off distance to get the radius within which the sound may be heard, and we use that radius to set the size of our collision sphere. We then look at actors that fall within that sphere of the type BP tree. We cast to each of those in turn to fill up an array of those BP tree reference objects. When the sound actually starts playing, we store that value in a variable, and then we read through each of the blueprint trees in our array, and we set each one of those to the current tree variable, and that allows us to use this function that executes the custom event within each tree. And our envelope values are mapped to appropriate ranges to control the wind speed and wind intensity. This is a nice example of how you can use real-time audio to drive visual events within the game.